Hi, Year 12. Okay, so now we're going to go through the long answer section of the test. So question 1 is about a bicycle moving up a slope, and you've got a cyclist moving up at an angle of 19 degrees to the horizontal, and it tells you that the mass combined of the cyclist and the bicycle is 85 kilograms. So you can see here that I have added a force arrow on the free body diagram to represent the weight which acts vertically down, and I know that the normal reaction force will always act at 90 degrees to the surface that is in contact with the object. So you can see R is at 90 degrees to the slope, and hopefully you can see through like triangles that the angle here is the same as this one. So I know that that's 19 degrees. And the first thing that you're asked to calculate is the component of the weight of the cyclist and the bicycle parallel to the slope. So you are taking the weight, you are splitting it into two components, this one and this one, at 90 degrees to each other. This is obviously the one that is parallel to the slope, so that is going to be W sine 19, which is mg sine 19, and you're told that the mass is 85, you know g is 9.81, and you've got sine 19, and when you calculate that on a calculator you should get 271 newtons for the first bit. And then you are then asked to calculate the normal reaction force on the bicycle from the slope. Now, just a reminder that this is the normal reaction force here. You know that the bicycle is not leaving the surface that it's travelling on. Oh, sorry. So you know that the normal reaction force up has to be equal and opposite to the component of the weight that is in that line. So you know that R is going to equal W cos 19, or otherwise the bike would move up and down in that line, and it doesn't. So this is going to be W cos 19, which is mg cos 19, which again is 85 times 9.81 multiplied by cos 19, and when you put that in a calculator you get 788 newtons. So that's the first two bits, and then the next bit has a little bit more to it. So you are told that at the bottom of the slope the cyclist has a speed of 5.5 meters per second, and the cyclist then stops pedalling and applies the brakes, which provides an additional decelerating force of 250 newtons, and you are asked to find out how long it takes in meters for the cyclist to stop. You've got no air resistance and no other frictional forces. So I've actually redrawn the diagram down first so that it will hopefully fit. You can see that I have included W sine 19, which is the component of the weight down the slope, which we worked out earlier in part A, because that is in the direction of the motion, so it is relevant to the question. And then obviously W cos 19 has no impact because it's at right angles. So you've got the component of the weight acting down the slope here, plus a 250 Newton braking force that has been applied, and you know that U is 5.5 meters per second. So the first thing we need to work out is the resultant force opposing motion. So F opposing motion equals 250 plus W sine 19, which you worked out earlier as 271. So the total of that is 521 newtons. Okay, now this is the combined force here that is causing the deceleration. Okay, now we know that acceleration is the resultant force over the mass of the object. So we know now to do 521 over, what was it, 85? and that works out to be like 6.129 something or other on the calculator, meters per second squared. That's not the final step though, because you're asked for the distance, so then you need to use the relevant Suvat equation. So we're going to use v squared equals u squared plus 2as, and we know to rearrange that to get s, we've got v squared minus u squared over 2a, sorry for going in the lines, equals s, and we know that v is 0 because it has to be at rest when it finally stops, obviously. So because you are doing minus u squared, you can effectively ignore the minus sign and just do u squared, and we get s is equal to 5.5 squared, minus would go away when you square it, so I'm just ignoring it, divided by 2 times the acceleration, which was 521 over 85. I'm leaving it in fractional form just there because it makes a more accurate answer at the end instead of truncating this number. And with that, you should get 2.47 meters. If you did a little bit of rounding and got it kind of like 2.5, that's absolutely fine, not to worry at all, so long as you've shown your working, that will all be good. So I think that is all of question 1. Yes, it is. Okay, question 2. Move this back up. Sorry for the prior working. Right, so you've got a ball released near the surface of the moon at time t equals 0. The point of release is on a straight line between the centre of Earth and centre of the moon. So I'm just going to sketch something for a second. So let's say this is the moon and this is the Earth. What they're saying in the question is the centre of those points is connected by this straight line. Imagine it looks like this. And it's saying that the ball is released near the surface of the moon. So it's not on the surface of the moon, but it's near to it. Okay, so let's say it starts here. And the point of release is then on a straight line. So it's then released along this line. Now the fact that it is closest to the moon means that it's actually it's dominated by the moon's gravitational field. So it's going to move towards the moon at this point. So we then come down and we see that we've got S against T, and as it is released from this point here, we see that the distance moved gets bigger, obviously, because it travels over time, but it gets more negative. So you can see the general shape of the displacement against time, and that should look familiar because it's obviously initially not travelling very far per unit time, but then later on it travels a big distance because it's accelerating, because it's in a gravitational field. So the first question is to explain why or what the significance of the negative values are. Now if you think about it, we can see that the thing is going to travel towards the moon, which means this is the negative direction and this is the positive direction. So what we can say is that moving towards Earth is considered to be positive, or moving towards the moon is considered to be negative. So what I'm just going to write here is the negative values show that moving up is considered to be towards Earth. Okay, now that basically means that we are defining up or down. When a ball is released, it falls down. We consider down to be the way an object falls. And so if the object is moving towards the moon, that's down, and therefore up is towards Earth. Okay, and then it asks you to estimate the velocity of the ball at t equals 0.8 seconds. Now we know that the gradient of a displacement time graph is velocity, but we cannot just take the point at 0.8 and read minus 0.5, because we don't have a straight line graph, we have a curve. Okay, so we know that the velocity is constantly changing throughout this time, so therefore we have to take the tangent at that point, not the value just from the points. So hopefully you can see I've drawn a tangent. I've then measured the y and the x distance of that tangent there, and I've put that here. So you will hopefully see that at t equals 0.8, which is here, the y change of the tangent is 1.4, the x is 0.8, no it's not, sorry, it's 1.1, it's this number here, excuse me, so that gives us 1.4 over 1.1, and the velocity is 1.27, and so all of that working that's up there will get you the marks for down here. So the velocity is the gradient of the tangent to the curve at t equals 0.8 seconds, and that is equal to 1.27 meters per second, or you could write that as 1.3 meters per second to two significant figures. So hopefully that makes sense. I might just keep this page handy for the next bit. We're just going to go straight up to here. So to then calculate the value for the acceleration of freefall close to the surface of the moon, well, I know that a is equal to v minus u over t. So what I need to do is look at some final velocity v, some initial velocity u, and the time difference between those two velocities. Now I've just calculated one of them here. Okay, and so what you then need to do is sometime later draw another tangent again. So at 1.8, if you track down, I then drew another tangent and I calculated the gradient again, and I got 2.8 meters per second. So this is the velocity at time 1.8, this is the velocity at time 0.8, so that was a time difference of 1 second. Okay, so v take u over t just becomes v take u, because t is 1. So all I'm going to do is the 2.8 minus the 1.27, and that will give me my acceleration. I'll pop it here again for you. So my v on the second tangent was the gradient was 2.8 meters per second, and that was at t equals 1.8 seconds. U was the first value that I collected, and that was let's call it 1.3 meters per second, and that was at t equals 0.8 seconds. So delta t is 1 second. So I'm going to do 2.8 minus 1.3 over 1. Okay, and I should be able to do that in my head, really, shouldn't I? Good grief. 1.5 meters per second squared. You might have slightly different numbers here, just from your gradient being slightly different from the tangent that you drew. So don't panic too much, but if your working is the same and you've got a similar number, you should be within tolerance. Have to make an apology, I did not check carefully enough. You can't do part C yet because you have not done Newton's law of gravitation, so apologies for that. I've taken the 4 marks off the paper, so it won't be considered part of the test. So not to worry, I will explain that another time. Here we go. Calculate the speed of an identical ball when it falls 3 meters from rest, close to the surface of Earth. Okay, so you now need to switch to a different planet, and you can take G to equal 9.81 on Earth with no air resistance. Okay, so this time you are going to do that again, and you're going to, lost my trail of thought, calculate the speed v, and you're going to use v squared equals u squared plus 2as, and that's what you're trying to calculate. You know it falls from rest, so u is 0, so therefore it's just equal to 2 times 9.81 times 3. And when you do that, you should get, put it on the calculator, and then you need to square root that to get v, so v is therefore equal to 7.7 meters per second. Okay, then we have to go back to the graph again, so I need to put that back on the screen. Sketch on the graph the variation with time t of the displacement s from the point of release when the ball is dropped close to the surface of the Earth. And then you're flipping the direction towards Earth this time to be negative so that it fits on the graph. So remember that previously we'd said if we were moving towards Earth it's positive. They're saying just consider it to be negative in this case so that you can make a direct comparison of the shape of the curve. So what I'm going to do is just choose 2 points. I'm going to choose t is 0.5 seconds and t equals 0.75 seconds, and I'm just going to use s equals ut plus a half at squared to get the value for s at those points, and I'm just taking the absolute value. So remember I'm doing s is ut plus a half at squared. U is 0 because the thing falls from rest, so this goes away, and this just becomes g, it becomes 9.81. So all I'm going to do is 0.5 times 9.81 times 0.5 squared, and that gives me 1.23. Forgive me for not showing all the working there, I'm just being a little bit lazy, I did it earlier. And then again for t is 0.75 seconds, so I'm doing 0.5 times 9.81 times 0.75 squared, and I get 2.8 meters. And then I can plot those points to give me a guide for the shape. So you can see t is 0.5, s was roughly 1.23, so that's about here. And then at t is 0.75, I get 2.8, which is here. Sorry, it's gone a little bit blurry. There we go. So you can see the general shape, and it's going to make a lot of sense because the acceleration due to gravity on Earth is greater, so it accelerates at a greater rate, so the velocity increases in a shorter amount of time, which is the gradient getting steeper in a shorter amount of time. And you know it starts from rest, so it starts from 0, 0, and then all you're going to do is hopefully sketch a curve that looks a little bit like this. Sorry, it's a little bit wobbly there, but you get the general idea. And that's the kind of shape that they're looking for. So that's number 2. So I would always make sure that I've got points that I've shown that I've checked. You'll get 1 point for 0, 0, you'll get 1 point for the general shape being underneath, and then you'll get 1 point for having it in an accurate place. So that's that question. So we move on to question 3. Here we go. Remove this, put a bit of space. So state the law of conservation of linear momentum, worth 2 marks. So the first point is to say that the total momentum of a closed system is constant. You could phrase that as momentum is the same before and after a collision in a closed system. That would be fine. If no external forces, which means forces that are not considered to be within the system itself, are acting on the system. Okay, so this is saying that it is constant, and this is saying why that will be the case if there are no external forces acting. So that's pretty just straightforward to remember. But then it gets a little bit trickier because they give you a graph and you get to do some calculations. So we're nearly there. You've got a toy car crashing into a wall and it rebounds at right angles as shown in the plan view. So you've got mu is the momentum before, and you've got mv for after the crash. And then it says the graph shows variation with time of the force acting on the car due to the wall on the collision. Now this is where I'd automatically be saying, okay, remind myself of the equation, equals mv minus mu. Before I even look at the graph, just write down what you know, linking those things together. Okay. So then you can see that during the collision, which is when the car is in contact with the wall, the force acting on the car and how it varies with time is shown here. So initially the force is increasing up to a maximum and then it decreases back down to 0. Hopefully you can see that this is going to be while the car is moving towards, or is in impact but moving into the wall, and this is while it's moving away from but still is in touch with the wall itself. The kinetic energy of the car is unchanged after the collision, so that means a half mv squared is constant, and the mass of the car is 0.8 kilograms. So if this stays the same and the mass of the car is just the mass of the car, then v must be constant, so u is equal to v. The velocity before is equal to the velocity after. That's important to understand. So I know that I'm asked to determine the initial momentum of the car. Now I'm going to repeat the equation and say ft is equal to delta p, which is equal to mv minus mu. I should also, for technicality reasons, put a minus sign here because actually they're equal in magnitude but in opposite directions. So I can express this as mv minus mu, because they act in opposite directions, becomes mv plus mu, which becomes 2mu, because v and u are the same in value. Okay, so the change in momentum is equal to 2 times the initial momentum. Okay, now I know that I am asked to find the initial momentum of the car, so I want mu. That's what I need to find. Okay, I've said that 2mu is equal to delta p, so mu must equal delta p over 2. Delta p is ft, force times time, over 2. Ft is the area of the graph, and so I'm going to find half the area of the graph. But remember that I need to find, so the delta p, which is the change in momentum, is this whole triangle, but I need to find half of that because I'm doing half of the change momentum here to find the initial. So I'm actually only interested in this section of the graph. That I want to find the area of. So you can see that this is 0.08, this is 24, it's a right angled triangle. I'll do it up here just so that we can see what we're doing. So the area here, A, is equal to 24 multiplied by 0.08 multiplied by a half, because it's a half of that area. And when you do that, you should get 0.96, and that is going to be a kilogram metre per second. You could also write that as a Newton per second, but it's a change in momentum. So I know then that this value here is the value of the initial momentum. It's half of the change in momentum, half of the area under the graph. So that is equal to 0.96. Okay. So following on from that, you're then asked to estimate the average acceleration of the car before it rebounds. Okay, so to do this, we need to look at the total change in velocity and the total time. Now we know that going into the wall, U was equal to the momentum, mu, divided by the mass. Now we just worked out mu to be 0.96, and we're told in the question that the mass is 0.8 kilograms. So initially it was moving at 1.2 meters per second. Now we know that the final velocity that it leaves the wall with is exactly the same because kinetic energy was conserved, but this time it's going to be negative to show that it acts to the left and not to the right. So then you're asked to find the acceleration, which is v take u over t is equal to minus 1.2 minus 1.2, and that occurred over a total time of 0.16 seconds. So that's minus 2.4 over 0.16 gives me minus 15 meters per second squared. It's really important to have the negative to show that it is a deceleration, to show that the acceleration acts in the opposite direction to the original direction of travel. So don't forget that. Okay, we've got to the last bit, I think. Hooray, we're nearly there. Where you are asked to sketch how the momentum of the car varies during the impact. You're not required to give values for momentum. Now, we basically know, I'm going to bring you back to this graph, that this section is when the car it has hit the wall but is travelling to the right, so it's kind of like squashing into the wall to the right, and then this section is when the velocity direction of the car has changed to be towards the left, and it's going back that way. So if you think about it, initially there's no force on the car, and then the car comes into contact with the wall at this point, and obviously the force value increases, and then at this point here, the turning point, the force then decreases back to 0. So this will be the point where the car then moves away from the wall and is no longer in contact. Force, F, is directly proportional to acceleration. So the acceleration of the car is getting bigger in magnitude until this point, and then it changes direction and decreases in value here. So we know that when we're plotting momentum against time, we know that the momentum in terms of direction changes at 0.08 because the force on the car changes direction at this point. It goes back the other way. So this is where we're going to have a turning point from positive to negative for momentum value. If you also think about it in terms of velocity, initially the car has a velocity of 1.2, so mu is some value, 1.2 times the mass. And then over time, when it's in contact with the wall, that value is going to decrease as it slows down towards the right, until it reaches a point where its velocity in the direction towards the right is 0 and it changes direction. Okay, and then the momentum increases because the velocity goes back up in magnitude because it's being accelerated to the left. Okay, now I am going to start mine from the positive side of the graph because I'm saying that as it's travelling towards the right initially, its momentum is positive, and then it should end up in the negative section because it's moving towards the left. However, if you did it the other way, that's fine, they would have allowed that. Okay, so at some point, let's go for here, this is mu, and then some point later, this is v. You don't need to quantify what that number is, but it's just important to get your general shape. We know that the momentum is equal to mu, or m times velocity at any point. And we know also that if the force increases up to 0.08, then so does the acceleration for a constant mass. Okay? And we know that the gradient of this graph is mu over t, which is ma. So the gradient is directly proportional to acceleration, so it's directly proportional to f. So if f was going up in the initial graph, then the gradient needs to increase or get steeper up to that point. Okay, so we're going to have a general shape that looks like this. Okay, and then it's just going to be a mirror image but negative on this side. So by 0.16 I should be about here. Okay, so you're sketching that general shape. So the gradient is decreasing, meaning that the acceleration is the gradient in magnitude is getting bigger, which means that the force is getting bigger. And then again, the gradient magnitude is getting smaller once you reach this point, which means the force is getting smaller, and will be horizontal here to represent 0 force. That's the general shape.